9.3 that discusses again convergence of the series, and we already know what that is. Series, the sum of infinitely many terms, right? And it turns out that what you can do is related to convergence of integral. The reason is we can definitely get the relationship with the integral because we know pretty well how to get, just a second. Just a second. So I'm back. So we have the integral that we know pretty well how to work with by now, right? And the series that actually something that we just were introduced with. So we have these two things that turns out behave very similarly. And that's the reason why we want to take a look at this so-called improper integrals. So what they do is they actually justify it by breaking area under the curve, which corresponds to definite integral with the pieces base 1 times height, which is our value of function. And we just saw in the previous sections that we have points on the graph of the function that will correspond to the actual elements of the series. So first, well, in this case, it's a A3, then A4, A5. Well, if there is a couple of extra pieces, such as A2 and A1, that never hurts for conversions, right? Because they, as long as they're finite value. But the point of story, if we have infinitely many pieces, so A index n, etc., a n plus 1, and then we continue this summation all the way to infinity, then we could relate the areas of these infinitely many rectangles with the actual integral, such as basis will be 1, so you will be multiplying by 1 your value of function, and if you multiply by 1, nothing changes, right? It's still same value of function. So that's the key idea why you want to relate it with integral, because it's really the same thing in terms of finding the area as well as sum of infinite series. So once you have that figured it out, then what they say is the area is behaving the same way as the sum of the series. So if we be able to find the area, then we'll say if series also going to be finite or convergence, if area is convergent, or infinite or divergent if area is infinite, right? So the series is also going to be divergent. And they give a couple of examples here that I wanted to take a look with you at. For example, here's the integral from 1 to infinity that you can calculate by using the substitution, right? If you were to substitute your denominator as an unknown u, then if you're going to take derivative of it, so let me write x squared plus 1, yeah, that's the replaced by your new variable letter u, then its derivative is 2x, right? So if you have derivative which is 2x multiplied by dx, that's going to be du. And of course, the 2 is something that we don't have in this original integral, so I'll just need to put it in denominator. We know with constants, it's always doesn't matter if something is different by the constant, so I could see there's no constant here, so I can take it away by bringing a 2 in denominator, and that's how we see that 1/2 that appears in front. And then we end up with integrating du over u, right? And that means you end up with a natural logarithm, and that's exactly what they have here. Natural logarithm of u, and instead of u, I put back my substitution, so it'd be natural logarithm of x squared plus 1. And now here comes the trick. Remember the trick? So you don't integrate all the way to infinity, but you stop at b, because then you turn this into the limit. So you can calculate the actual value of the ln and then plug b in it. And then when you take a limit, you will see if that's infinity or not. And in this case, it is infinity because what you do is subtract the ln of 2, the lowest value, lower value is 2. And because it's starting from x squared plus 1, so you put 1, the ln of 1 squared plus 1, ln of 2. There's a lower with a minus, and with a plus it'd be ln of b squared, and ln of b squared is infinite. So that one is going to infinity, and that's why the whole thing is maybe divergent or infinity, and that's the point of the story. So the integral test, that's how it's called. Integral test does not really give us the way to see what the actual sum of the series is, but it enables to see us if it's divergent, like in this example, or if it is convergent, like example 2, there is a convergence considered also, because if you integrate that fraction with x squared plus 1 on the bottom, it's going to be arctangent, right? And you get arctangent b, arctangent 1, and turns out arctangent b goes under pi over 2, so it'd be arctangent of pi over 2 minus arctangent 1, which is pi over 4, so it is pi over 4, but it does not mean that the sum of this series is actually pi over 4. What it means only is that series conversion. So whether the series, the sum of infinitely many terms, is convergent or finite, or not finite or divergent, we'll be able to see using the integral. And our integration skills are being utilized in that case, and this is the whole point, I guess, of this process, to see if it's convergent and divergent. And I think there is very interesting and useful in the future little statement that we can see that's coming out from this integral story. So if you have so-called harmonic series, which is dealing with adding 1/2, 1/3, 1/4, and so forth, this is always going to be divergent. But once you, so it's like series sum of 1 over n. But if your power of n will be bigger than 1, because in this particular case, it's power of n is equal to 1. So first power of n. So it's like n to the first. But if n is raised to the power a little bit bigger than 1, it is always going to be convergent. So it's like a borderline. Harmonic series divergent, and if power of n is a little bit more than 1, convergent. And the reason is an antiderivative, because if you take the antiderivative, then the power is going to be p plus 1. So if p is negative, so if number is a little less than 1, so if you add 1, then it's still going to be in denominator. So we can actually visualize it here. So if you actually take pains and try to find the antiderivative, you will be able to see that. So I can, there is no example. So I can try to do one exercise and then I will let you go as I promised today a little early because I must. Well, I'm sorry, but I must be at some place and I don't have a choice. So I'll have to leave in about a few minutes. So, anyways, what if you're trying to look at the harmonic series 1 over n? So it's n's power and denominator. Then I need to consider the corresponding integral of 1 over x. And I'm sure you're already familiar how to take antiderivative of 1 over x. It's ln, right? Derivative of ln is 1 over x, and antiderivative of 1 over x is ln. So if you try to find the antiderivative, it's going to be ln of x. And you say, Alex, this is absolute value of x. Yes, but since our antiderivative is taken from 1 to infinity, then the problem with domain is not going to appear, right? So you're going to have to do the following. So you're going to integrate it from 1 to some particular number b, right? And then what you do is approach this b, send it to infinity. So you're taking not much room, but I'll try to fit limit when b is sent to infinity. So that way you have ability to plug b in, because ln of infinity, we don't know what it is, but we know what ln of b is, right? So we're gonna end up with taking that limit and upper and lower limit. So fundamental theorem of calculus says that you take ln of upper, which is b, minus lower, which is ln1, and when b approaches to infinity, we have infinity, right? So when b, see the most important part when you take a limit, see what your variable letter is going to be approaching to. If it's infinity, well, then the entire ln also approaches to infinity. Because logarithm increases without a bound, even though it does it slowly, but it is still approaching to infinity. And ln of 1 is 0, right? Let's say, sure. Yeah, you can put it in the calculator if you forgot what ln represents. So this is equal to infinity, which is mean that our series is divergent. When we don't write the sum is equal to infinity, we say it's unbounded or divergent. And I guess the integral approach is probably the best approach to justify it. So one can say, if here we have 1 over n squared, then when you start to take the antiderivative, you're going to end up with something convergent. So probably it's a good idea for you to try to do this sometime tonight or tomorrow, and I think I will continue with that on Thursday. So the moment I must stop, I don't want to stop, but I have to. So I'm sorry that I have to stop at this stage, but the good news is we'll continue it on Thursday. All right. So thank you so much for paying attention to this.